Hello, welcome to the lecture on network theory. We are continuing with Thevenin's and Norton's theorem, and we'll be doing category 2 and category 3 type of problems in this one. So category 2 means both dependent and independent sources. So let's say a question right away. Have a 4 ohm, 5 Vx. Vx is defined like this: 2 ohm and 3 volt. So the question is to find that's right here, find Thevenin and Norton equivalent circuit. Okay. So right away, what do we do? First, one thing we have to do is we have to find ISC. Okay. The other thing is we have to find the VOC. Okay, that is the thing we have to do. So let's start with the VOC. For VOC, I am assuming that there is a current I here, and the current will be flowing like this, in this way. Okay. So taking that thing and writing the loop equation, sorry. So minus 3 plus I into 2 plus 5Vx plus 4 into I equal to 0, right? And Vx we can define as, how do we define Vx? Vx is this much, right? Vx is 3 minus, Vx is 3 minus 2I, and this we can substitute here. Okay. So this we can substitute here. So it will be minus 3 plus this 2 plus 4, 6I plus 5 into 3 minus 2I equal to 0. This will give I equal to 3 ampere. Okay. From this, what is VOC? VOC is this I into 4, which is 3 into 4, that is 12 volt. We have VOC as 12 volt. Okay. Now we have to find ISC. For that we are taking shorting this, short circuiting this one. So this resistor will be invalid, and instead of using I will be using ISC. Okay. To find ISC, again 3 minus 3 plus 2 into ISC plus 5Vx equal to 0. Again Vx equal to 3 minus 2 ISC, and substituting it here we get minus 3 plus 2 ISC plus 5 into 3 minus 2 ISC equal to 0, and solving for that we will get ISC equal to 3 by 2 ampere. So then once we have it, we can write IN equal to Rn equal to Rth is equal to VOC by ISC, which is 12 by 3 by 2 will be 8 ohm. Okay. So that is, we have Vth equal to VOC which is 12 volt. We have IN equal to ISC equal to 3 by 2 ampere, and we have RN and RTH is equal to 8 ohm. So writing both the Thevenin and Norton equation, equivalent circuit. Always be careful when you are writing the polarity. Here we have taken VOC like this, plus sign should come at A. So the plus sign of the source should be corresponding with A, 8 ohm and 12 volt, right? And the Norton equivalent is again we have A and B, right? 8 ohm, 3 by 2 ampere. Again, be careful regarding the arrow, the direction of the current. Current is going from A to B. So again, it should be like this. So the arrow should be upwards. So this is the Thevenin circuit. This is the Norton, and both of them are equivalent and duals. Okay, so this is how you solve a category 2 problem. You find VOC and VIC. So like if you're given a category 2 problem, no matter whether you're asked to find the Norton or Thevenin equivalent, doesn't matter, you have to find VOC and ISC. Otherwise you won't be able to find the equivalent resistance. But in the earlier case, that is in category 1, if you are asked to find the Thevenin equivalent circuit, you just need to find VTH. You don't have to go for IN or ISC or anything like that, and vice versa. Okay. So now let's move on to a category 3 problem, which is only dependent sources. Okay, now let's write a question right away. Okay, let's write a question. A, B, V0, 1 ohm, 2 ohm and 4 ohm. Okay, so when you are thinking of the equivalent Thevenin equivalent or Thevenin equivalent or Norton equivalent of a circuit with only dependent sources, ultimately you will only get some sort of resistance. There won't be any current source or voltage source, because dependent sources always require some independent source to energize it, right? Because this this dependent source is depending on this V0 to energize it, or it depends on the value of this V0 to determine its value. Okay, so you cannot simply, because there is no other independent sources, by itself this won't have any value. It is a dependent source, right? So ultimately when you are having a category 3 problem, your equivalent Thevenin or Norton circuit, either way it will be just the equivalent impedance or equivalent resistance across A and B. So whatever technique we are using here, we can use that to find the resistance or impedance between any 2 terminals having some dependent source. Okay, so here what we do is, the question is find Thevenin and Norton Okay, so what we do is we take the circuit, right, we have A and B here, our 4 ohm, 1 ohm, V0, 2 ohm. Okay, and what we do is we apply an external source. Okay, we are applying a external source. Here I am applying a current source. You can apply a voltage source, it depends on the problem and your interest. Okay, the thing is that when we are applying a source, the value of the source should be known. I am taking it as 1 ampere for convenience. Okay, I am applying a 1 ampere current source. That means 1 ampere will be flowing this way. Okay, let's just remove the terminal names, otherwise. Okay, 1 ampere current is flowing through here. So ultimately, how do you find the R equivalent? Okay, you have to find the V here, right? V. Let's call it Vx. Okay, so R equivalent will be Vx by 1. Vx by this current. This current is 1 ampere only, so Vx by 1 will be R equivalent. So that is why this 1 ampere I took 1 ampere here, because you can directly get. You won't have, once you have Vx, then you won't have to do any other manipulations. Okay, so we have 1 ampere here. Okay, 1 ampere here, and we have 2 VO here, so it will be 1 plus 2 VO coming this way. Okay, so now what do we do? Now we just write the current equations. Okay, so we have 1 plus 2 VO current coming this way, and it is creating this V0. So we can write, okay, we can write V0 is equal to 1 plus 2 V0 into 2. Okay, from this we will get V0 is equal to minus 2 by 3 volt. Okay, so this will be 2 plus 4 by that is 2 plus 4 V0. V0 equal to 2 plus 4 V0. You can shift it this way and rearrange. You will get V0 equal to minus 2 by 3. Okay, that we have. And now what is Vx? Vx is this much, right? Let's just use another color. Vx is this much. Okay, so we can write Vx as 1 into 4 plus 1 plus 2 V0 into 1 plus V0. Okay, that is Vx, and substituting this minus 2 by 3 here, what we get, we will get Vx equal to 3. We will get 3 volt. Vx equal to 3 volt. You can substitute and try. So we have Vx, and what does that give? R equivalent equal to Vx by 1, which is 3 ohm. Implies our Thevenin equivalent Vth is equal to 0 and In equal to 0. We'll just start a new page. So we have our Rn equal to Rth equal to R equivalent, that we found out as 3 ohm. Okay, now the thing is that since only dependent sources are there, it implies it once we remove this external source that we use to find the equivalent resistance, then there are no other internal sources to energize this V0. We just found the response of V0, right? Since there is no other internal sources, there won't be any VTH, there won't be any I Norton. Okay, now let's write anyway. We have 3 ohm. This is a 0 volt source. Okay, 0 volt source. And what is the internal resistance of the ideal source? It is 0. Implies this will become just a 3 ohm resistance. Similarly, we can write A, B, 3 ohm. So this is Thevenin, this is Norton, 0 ampere. And what is the internal resistance of a ideal current source? Is it infinite? That means this is an open circuit. So again, this will also become A, B, 3 ohm, right? So basically what I'm trying to say is, for category 3 problems, that is only when only dependent sources are there, Thevenin and Norton circuit, equivalent circuit, is simply the equivalent resistance or impedance of the given circuit. And for that we are using this method of applying an external, not ideally, better to use a unit source, unit current source or voltage source depending on the situation. So you apply an external source, you find the response of the system, and from the response you find the ratio, the voltage by current ratio, and that will be the R equivalent of the network across the given terminal. And our equivalent voltage Thevenin and Norton circuit will be simply that resistance. And this method you can apply to find the equivalent resistance or impedance between any two terminals having a dependent source. So you can suppress the independent sources and you can apply this method. Okay, so that is with some examples for Thevenin and Norton equivalent circuits. And with this I am stopping the lecture on Thevenin and Norton circuits. More problems will be posted in your classroom. Thank you.